Hello everyone, I'm Rajaram Manohar Joshi. I'm a Master of Science in Computer Science student at UC Davis, and this is my master's project presentation on ResTier, a tiered storage engine I designed and implemented for ResilientDB. This work was done under Professor Sadogi at the UC Davis Expo Lab. So, what is ResilientDB? ResilientDB is uh, a high throughput distributed ledger built on scale-centric design principles, and it is aimed at democratizing and decentralizing computation. And this is the system that ResTier is built on top of. And this is a now since it was originated at UCS's Expo Lab, and it is now an Apache incubating project. Its core design uses Byzantine fault tolerance consensus protocols, and it handles modern scale, which makes storage management a critical concern as data accumulates. So why ResTier? Let's understand the present scenario and the motivation for this project. So ResilientDB today uses a single level DB instance for all storage. So the level DB is the underlying storage engine for ResilientDB. So it uses each node within a ResilientDB would use a single level DB instance for all storage. And because blockchains are append-only by design, that storage grows unboundedly. And since there is no existing way to offload historical data, and uh, also the historical data is rarely accessed or queried. So this leads to SSD bloat over time as the data scales. Why ResTier? The next part is the proposed solution. So ResTier addresses this by introducing IPFS as a cold tier for archival data and migrating key value pairs asynchronously based on configurable checkpoints. And why IPFS? IPFS is a natural fit here. So it uses content addressing model, and that gives us trustless verification, built-in deduplication, and no vendor lock-in. So it's an open source protocol. And since it is mathematically verified the data, so that again uh, works on the same philosophies that ResilientDB works. So this is the problem statement that I had for myself while before working on this project. So I wanted to design and implement a tiered storage engine for ResilientDB that transparently migrates historical data from hot storage to IPFS. So hot storage, I'm saying hot storage, it means memory DB or level DB, which is the existing first layer of storage. And IPFS, I would call as the cold tier or the cold storage. So, and this would be completely transparent to the existing PBFT write path, and there would be no effect on the consensus or the write path latency, no added latency. And at the same time, the cold reads need to be fast. So they still need to be fun operations, and the system must survive crashes without losing any data. And the constraints I had for myself was that each PBFT replica within ResilientDB migrates independently, doesn't depend on other nodes for migration, and handles its own um, indexing, its own migration logic, everything. And there should be no data loss at all. And even the cache within level DB should be invalidated on eviction from level DB. So, and the write throughput and read latency should not be affected. So this would result in lower storage costs and over long-term period, which would be validated in the further results in the next slides. So here is the system architecture. So the architecture has 3 storage tiers within each ResilientDB nodes. So the hot for active data. So this is not cache situation. So this is just whatever recent data is there, all that is there in hot. So recently written data, and this would be the implementation would be memory DB or level DB. I've abstracted that into calling it hot storage, and the tiered warm and cold are only when the tiering is enabled. So warm stores the mapping between the keys that is within memory DB or level DB and the content ID of the actual block when in IPFS. So this acts as a secondary indexing layer between these two tiers. So this warm tier actually does not store any data, it just stores the mapping between these two. So the tiered storage interface, that is an abstraction over the existing storage interface. So it has a migration thread which runs asynchronously. It has an in-memory hash index, which is an in-memory version of the level DB manifest, and the actual level DB manifest as well that acts as the secondary indexing layer. And this is within each node. So each node will have its own memory DB or level DB instance, and it will have its own manifest, and it will have its own IPFS sidecar. So even though uh, the each IPFS within on a node will be attached to its own node, so as a sidecar. So all communications happen from here to here. There is this does not talk to IPFS of other nodes, and it does not depend on that either. So these are the four storage modes that ResTier supports. So it can be deployed across different environments. So from a simple in-memory memory DB setup for dev testing, or this is the fastest, that these two levels already exist, these two implementations. So memory DB and level DB already exist. These two are the tiered storages that are being introduced as part of this project. So the hot tier is the level DB and cold tier is IPFS here. And in this case, the hot tier is memory DB and the cold tier is IPFS. And we are interested in this mode because this gives us the most accurate representation of how the storage costs are reduced, or we can evaluate how much we save on the SSD's storage with this migration strategy. Going ahead with the write and read path. So this is the write path, which indicates no overhead. So this is the exact existing flow. So writes go straight to the hot tier. So after PBFT consensus ordering and agreement, it goes through KV executor. It goes straight through tier storage interface to hot storage interface, and whatever the implementation of the hot storage is, either memory DB or level DB, it does an immediate write. And this is a cursor that is atomically updated along with this write. So this is the one that actually tracks the most recent write sequence, and it migrates based on configured checkpoints and thresholds. So the writes do not go to IPFS directly. So since the writes don't talk to IPFS, there is no added latency or anything. It is exactly as it currently is. So it just goes straight through to memory DB or level DB. And coming to the read path, so read path is slightly more um, uh, complex, where we have a fallback mechanism. So currently what it does is that the get value function directly calls memory DB or level DB and returns the value. So for now, if in this case, during once there is migration has been done for a particular key, so if it is found in the hot tier or core hot tier, which is memory DB or level DB, if it is found, it directly returns. If it is not found, then it falls back to the cold tier, where it gets the CID from the in-memory hash index, and it fetches the block from IPFS and then returns the value. So that is pretty straightforward. So yeah, this is the added logic, which is resolving the CID from the hash index, and getting it from actually fetching the value from IPFS. So this introduces a slight latency overhead, which is compared to just reading directly from MemryDB or LevelDB, this adds some read latency. Since this is a network call to a sidecar, but from the client's perspective, the this latency gets completely hidden because because of the network latency from the client to the ResilientDB node proxy and then to all the ResilientDB nodes and the actual read operation. So all these are all still network calls. So um, the latency gets hidden in whatever testing that I have done. So read from hot tier or read from cold tier are pretty much comparable. Going ahead to the migration flow. So the migration runs entirely in a background thread, so which is completely decoupled from the write path. On each poll cycle, the migrate cold data, this method, this checks whether enough checkpoints have passed. So based on this calculation, the threshold, the current sequence should be the from the checkpoint minus, which is the last migrated checkpoint from this threshold. If it is done, so all those eligible keys are batched and migrated at once to reduce the number of network calls. So, and for each eligible key which needs to be migrated, so this is the order in which it happens. So first it is uploaded to IPFS and a CID is returned from IPFS, and that CID is added to the in-memory hash index, and it also is updated in the level DB so that we don't lose the mapping between the key and the CID. Since it is IPFS is content addressed, if we lose the CID, we lose the value. So storing this in just in in-memory hash index would risk us to since in-memory hash index is in memory, it is ephemeral. So if in case of crashes, we might lose CID. So we also have to save the manifest to durable storage, which is level DB. So once that is done, I also evict the key from the hot storage so that this is the point where we save space on level DB. So once the migration has been completed and it has been verified, the key is deleted from the hot storage. And also it is the LRU cache on the level DB is also invalidated. This is another scenario where if another transaction happens which updates the key from a previous key, it updates the version of the key, the value of the key, and that creates since the IPFS hashing happens on both the key and the value. So another entry is created because it's not the same data content in the IPFS. So what we have to do is that the stale CID, which is contains the old data, if the key was updated, as in the value of the key was updated, then I have to unpin or like delete from IPFS that particular stale CID so that and update the um, in-memory hash index and manifest as well with the new CID. So once it is unpinned from IPFS, it is also it is ready for garbage collection. So we save space there as well. So this is, and then it sleeps until the next poll cycle. So this is the overall migration flow. So coming to crash recovery, I analyzed 4 crash windows during the migration sequence and verified that in every case, either the key is still readable from the hot storage or is fully accessible via the index and IPFS. So the worst case is a safe duplicate where the key exists in both tiers, such as this case where after the hot delete, if the node crashes, then the data uh, Oh, sorry. So if in this scenario, if the after the IPF data has been uploaded to IPFS and has been added to the index, but before the cache has been invalidated or before the hot tier has been evicted, so if it crashes, if the node crashes at that point, then the state is that the data is present in both the IPFS and in the hot tier. So that is the worst case scenario, which is quite rare, but it does not result in loss of data. The data is always safe. So in conclusion, ResTier successfully delivers tiered storage for ResilientDB with no write path overhead, of one cold reads, and zero data loss. It plugs into the existing PBFT consensus infrastructure without any consensus layer changes, making it a practical and deployable solution. So this is a observability dashboard that I built for my STR benchmarking. So this is a simple experiment that I ran for 10,000 keys, where it is a simple linear writing script. So it just iterates through the keys and appends, posts the write operation to the ResilientDB client proxy. And you can see that it goes through uh, all the 10,000 keys lead to 1.6 MB of level DB for non-tiered. And for a tiered instance of level DB mapping to IPFS, so the same 10,000 keys lead to a total of 955 KB of level DB space and the 15 KB of IPFS space. So it is also reduced in size, which is because of this is excluding the IPFS internal um, storage, which it needs to maintain metadata and stuff. So this is purely the size of the data that it has, but this includes the total level DB disk usage. So for 10,000 keys, we can see that it almost gives a 22% storage savings with 5,200 keys out of 10,000 migrated based on the checkpoint and um, threshold configuration that I gave while running this experiment. So we can see that for tiered versus non-tiered comparison, so this the war manifest itself stores around 32 330 KB of data. So if you just see the purely the difference between the data in the level DB for tiered versus non-tiered, for 10,000 keys it is 1.6 MB versus 955 KB. So the remaining 320 KB is the tiered manifest. That is the mapping between the key and the IPFS CID that is stored over there in level DB. So overall, it uses much lesser space than non-tiered, even for 10,000 keys. And this number is going to just grow as this number of keys grows. So let's also see the comparison of this. So you can see that it gives around 43% net storage savings for just the level DB um, level space in level DB. And per node also we can see that the it uses around 416.9 KB and the tiered one for per node is 238.7 KB. Yeah, pretty much. And yeah, the migration also shows that it is around 3 to 4 bytes per key, the actual value of the thing in IPFS. So it took a pretty long duration because it is limited by the power of my system hosting 4 nodes and each node having its own IPFS tier. So here also in this graph, you can see the disk usage over time. So this is disk usage versus time in seconds. So as the time passed, the disk usage just kept on increasing linearly for non-tiered. For tiered storage, you can see that it kept increasing as well. It kept increasing linearly for the tier for the level DB, but the manifest kept on increasing. And once the once it was migrated, these also deleted from the hot storage, right? So that immediately when we delete it, it does not clear up space in the level DB. So it just keeps on piling up. It is garbage collected only automatically. So I had to, for the sake of this experiment, to see the actual space saved, I had to also um, uh, in my testing, in my benchmarking script, I also cleared out the level DB garbage collection. So that resulted in this drastic drop for the manifest as well. So yeah, that's pretty much about it. I had a great time working on this project, and I thank everybody who had helped me into this. And you can reach out to me and email me or anyone from the team or if you have any questions. Thank you.